In the last lecture, we defined what is meant by a power series, and we proved that a power series converges absolutely in its disk of convergence. We also remarked that a power series behaves very similar to polynomials in its disk of convergence. We begin this lecture by proving that a power series is holomorphic in its disk of convergence, and that just like in the case of polynomials, we can obtain the derivative by differentiating the power series term by term. So let's begin by stating down the theorem. Let summation an z minus z0 to the power n be, so let f of z equal to be a power series around z naught with a disk with a radius of convergence r. So recall that summation a n z minus z0 to the power n converges in dz0r, and the limit is what is being captured by f of z. So in particular, f is now a function from dz0r into the complex numbers. Then this function f is holomorphic. Where is it holomorphic? It is holomorphic precisely in dz0r, and the derivative f prime of z is given by the power series summation n a n z minus z0 to the power n minus 1 which has the same radius of convergence as the power series we started off with, which has a radius of convergence r. So notice that the theorem is actually capturing all that I said. F is holomorphic on dz0r. Not just that, we obtain the derivative f prime at any point z by differentiating summation a n times z minus z0 to the power n term by term. Let's give a proof of this theorem. We will not be let us first check that this power series that we have written down here, this particular power series, it indeed has a radius of convergence r. We will bother about whether it is the derivative or not later. Let's first focus on that particular power series. So let's give a proof by let's begin by considering the power series summation n a n z minus z0 to the power n minus 1. This is from n is equal to 1 to infinity. Just rewriting it, we can say that this is n equal to 0 to infinity n plus 1 a n plus 1 z minus z0 to the power n. So what is the radius of convergence of this? Then r prime which is the lim inf as n goes to infinity of mod of n plus 1 to a n plus 1 to the power minus of 1 by n. This is precisely the radius of convergence of the power series written here. Our goal is to show that r is equal to r prime. So to do that, let me first give you an exercise from your real analysis course. It is to show that limit as n goes to infinity of n plus 1 to the power 1 by n is equal to 1. Yeah, you may mimic the proof used to prove that n to the power 1 by n converges to 1. And tweaking it, you will be able to prove this. So let me leave this as an exercise for you. The claim which we will be proving is that let R0 be equal to lim inf as n goes to infinity of the second term a n plus 1 to the power minus of 1 by n. Suppose this number is equal to R0, then R0 is equal to R. It is the same as the radius of convergence of the power series we started off with. Let us give a proof of this. Let us first prove that R0 is less than or equal to R. And in order to prove this, consider the power series that we started off with. Summation an z minus z0 to the power n. This is the power series we started off with. And this can be rewritten as a0 plus z minus z0 times summation an z minus z0 to the power n minus 1. N is going from 1 to infinity. Now for z in dz0r0, for z in dz0r0, what do we know about the power series that we have just underlined? This particular power series, as you can note, has a radius of convergence r0. So here r0, this particular point z is in a disk of radius r0 around z0, and in particular this series converges, right? Hence summation mod an z minus z0 to the power n. This is less than or equal to mod of a0 plus mod of z minus z0 times summation mod an mod z minus z0 to the power n minus 1. And we know that this converges, and hence this particular series as well converges. This implies that summation an z minus z0 to the power n converges, in fact absolutely, in dz0 r0. But that immediately tells us that r0 is forced to hence be less than or equal to capital R. Because for every point in the disk of radius r0 around z0, the series converges. And we know that outside the closed disk of radius r, summation an z minus z0 to the power n diverges. So r0 is necessarily less than or equal to r. Let us now prove the reverse inclusion. In order to prove the reverse inclusion, let's consider some point z in dz. Let's begin by considering some point z in dz0r. This means that summation an z minus z0 to the power n converges, isn't it? Let me now write down summation an z minus z0 to the power n minus 1. So for z not equal to z0, let's also put in this extra assumption, because for z0 we know that it is equal to the constant term. So for z not equal to z0, what do we know? This is less than or equal to 1 by mod of, maybe let me put an absolute value, this is z minus z0 into summation an z minus z0 to the power n, where n is from 1 to infinity. Well, we have just used the triangle inequality here to be precise. So we use the triangle inequality to, maybe I shouldn't skip steps. Let me just write down all the steps so that there is no lack of clarity. This is less than or equal to summation mod an z minus z0 to the power n minus 1. But remember that we know, what do we know? We know that summation an z minus z0 to the power n, this converges absolutely. because z belongs to dz0r, and therefore we can write this is from 1 to infinity. So this is equal to 1 by mod z minus z naught times summation n is equal to 1 to infinity a n mod z minus z0 to the power n. We can now further add a positive term to this and write this as, well, this inequality, or this equality rather comes up because summation a n z minus z0 to the power n converges absolutely. This actually is an equality, so I need to write it as an inequality. So this is equal to this, which is in particular less than or equal to summation n is equal to 0 to infinity mod a n z minus z0 to the power n, which converges, and mod z minus z0 is just some constant. So this implies that summation a n, so this is from n equal to 1 to infinity, or n equal to 0 to infinity of a n plus 1 z minus z0 to the power n converges in dz0r. But we know that r0 is the radius of convergence of this particular power series, and therefore this implies that r is less than or equal to r0, and hence both the inequalities imply that r is forced to be equal to r0. So what have we established? All the work was to establish this particular claim, the claim that the lim as n goes to infinity of mod a n plus 1 to the power minus 1 by n is precisely equal to r. So now we have a sequence. So another exercise for you. This is also a basic real analysis exercise. Let an and bn be, maybe I shouldn't use an and bn, might be confusing. It's just an exercise. This is just a general exercise. These ans needn't be confused with the coefficients which I have written above. Let an and bn be positive real numbers such that an converges to a, where a is a positive number. So as of now we are in real number, in the real setting. A is positive, and suppose the lim n as n goes to infinity of bn is equal to b. Then the exercise demands that we prove the following: lim n as n goes to infinity of an times bn is equal to a times b. This is precisely the setting we are currently in. Observe that n to the power n plus 1 to the power 1 by n converges to 1, and the lim n is exactly equal to r, lim n of mod n plus 1 to the power minus 1 by n. And therefore the lim n of n plus 1 into mod n plus 1 to the power minus 1 by n will also be equal to 1 times r, which is equal to r. So applying the exercise by using this exercise, we can conclude that the radius of convergence of the power series summation n a n z minus z0 to the power n minus 1, that n is from 1 to infinity, is r. Okay, so we have done half of the job. The other half is to prove that indeed the derivative of the power series we started off with is indeed this particular power series. To do that, let's consider f of z, the Newton coefficient. Now consider the quotient, not coefficient, Newton quotient. Basically f of z minus f of let's try to prove uh, the derivative at a point z1 as being equal to the expression given by this power series. So fix z1 in dz0r, and we will be looking at this quotient. This is the quotient we are interested in, and we will take a limit as z goes to z1 in dz0r minus z1. But before we talk about limit, let's see what this quotient will look like. This is going to be the sum a n z minus z naught to the power n minus z1 minus z naught to the power n by z minus z1. We can write it in this manner precisely because summation a n z minus z naught to the power n converges to f of z, and summation a n z1 minus z naught to the power n converges to f of z1. Because these two series converge to respectively f of z1 and f of z and f of z1, f of z minus f of z1 precisely becomes the series to the right. Now let's do the basic arithmetic to conclude that this is going to be summation a n times this is equal to 0 to infinity, and each of these will reduce to the following. N minus 1 plus z minus z0 to the power n minus 2 times z1 minus z0, going all the way up to z1 minus z0 to the power n minus 1. Notice that the z minus z1 cancels with z minus z0 minus z1 minus z0, which is equal to z minus z1. Now we shall show that the limit as z goes to z1 of this summation exists. To prove that, we cannot just take the limit inside the summation. So what is our goal? So we want to show that limit as z goes to z1, where z belongs to dz naught comma r minus z1 of summation a n times z minus z naught to the power n minus 1 plus, I will not write all the intermittent terms, let me just write it this way. This is equal to summation n a n z1 minus z naught to the power n minus 1. This is precisely what we would like to show. And if we can interchange the summation and the limit, then we would be able to establish what we want to show. However, that's more subtle. Let's justify that we can indeed interchange the sum and the limit. And in order to do that, let's define the function g of z to be exactly this function, summation yeah. So let me just do it from 1. So for n is equal to 0, z minus z0 to the power 0 is 1, z1 minus z0 to the power 0 is also 1. The terms cancel out, so the sum indeed starts from n equal to 1. And therefore, let me define g of z to be equal to n from 1 to infinity a n z minus z0 to the power n minus 1 plus z minus z0 to the power n minus 2 times z1 minus z0 plus all the way up to z1 minus z0 to the power n minus 1. Okay, so let R1 and R2 be such that mod of Z1 minus Z0 is less than R1, which is less than R2, which is less than capital R. So Z1 is in the disk of radius R around Z0. So there are certainly, you can certainly take R1 and R2 two positive real numbers which satisfy this condition. Also, let epsilon be such that dz1 epsilon is contained in dz0 R1. So dz1 epsilon is a small disk around z1 such that it's contained in the smallest of the disks of radius r1, r2, r3, or whichever you consider. The smallest is r1, so it is contained in r1. Let us now study what we can talk about the terms which appear here. Let's analyze each of those terms. And then we will be able to conclude that mod of an z minus z0 to the power n minus 1 plus z minus z0 to the power n minus 2 times z1 minus z0 to the power 1 plus up to z1 minus z0 to the power n minus 1. Each of these, the first thing to conclude is that this is certainly less than or equal to mod of an times n into r1 to the power n minus 1. This is certainly something which we can conclude, because z and z1 both are inside the disk of radius r1 around z1. So the distance is certainly less than or equal to r1, and there are n terms which feature over there. We also know that the liminf of mod an to the power minus 1 by n is equal to r, and therefore there exists capital N such that, so this is since liminf n going to infinity of mod an to the power minus of 1 by n is equal to r, and r2 is less than r, we have an n such that for all n greater than capital N, mod of an to the power minus of 1 by n is greater than r2, because if it was not the case, the liminf would have been less than or equal to r2. So this is certainly getting satisfied, and rewriting this tells us that mod of an is less than 1 by r2 to the power n. That is good, because if you go up, what this tells us is, so this is what we would like to focus on right now, that will be bounded. So let me not write it again and again, it's a big expression. This is less than or equal to n times r1 by r2 to the power n. Notice that r1 by r2 is less than 1, and summation n times r1 by r2 to the power n converges. And by Weierstrass M test, hence by Weierstrass M test, summation an z minus z0 to the power n minus 1 plus z minus z0 to the power n minus 2 times z1 minus z0, and so on this. Okay, this is all true. Okay, let me finish it and then tell you where this is all true. This is all true. Notice that this is all true when z is in dz0, in dz1 epsilon, right? So let me see where that should be put into. Okay, let z be in dz1 epsilon, then there is no confusion. All these things go through and we have this result as well. this converges uniformly in dz1 epsilon. Remember, this is the exact domain where our g of z was defined, right? It converges uniformly to g of z. Being a limit of continuous functions, g of z is also a uniform limit of continuous functions. G of z is a continuous function. Since g of z is continuous, we have limit z going to z1 of g of z is equal to g of z1. And that's precisely what we want to prove, isn't it? Because g of z1, if you notice, this translates into the following, i.e. limit z going to z1 z in d z0 r minus z1 of f of z minus f of z1 by z minus z1. This is equal to g of z1, which is equal to summation n an z minus z0 to the power n z1 minus z0 to the power n minus 1. And that's precisely what we were trying to prove. Since our choice of the point z1 was arbitrary, we can say that it's complex differentiable at every point in dz0r, and hence thus f of z given by summation an z minus z0 to the power n is holomorphic on dz0r. So for sure we know that in this disk of radius r it converges. Let us now look at some consequences of the theorem that we have proved. This theorem, actually we have proved quite a lot in this theorem. One of the first corollaries is that we can get hold of the coefficients explicitly in terms of the derivatives of f. So let f of z be equal to summation an z minus z0 to the power n be defined on dz0r, where let f of z be this on dz0r, where r is the radius of convergence of this power series. Then we have an explicit expression for the coefficients. An is given by fn of z by n factorial. Let's give a proof. So the first observation in the course of this proof is to notice that if we have a power series, summation an z minus z0 to the power n, we look at its derivative, the complex derivative, that will also turn out to be a holomorphic function, which is a power series whose radius of convergence is again r. And by applying the theorem to the derivative again, we get to conclude that the derivative is also holomorphic. So in particular, a power series is infinitely differentiable. We can differentiate a power series to any order, and we explicitly know what the power series will look like. That's the first exercise that I would like to give for proving this corollary. Prove that fn of z, let me give you an explicit expression for that. This is going to be equal to summation n, okay, fm of z. The nth derivative of f is n into n minus 1 into n minus m into z into an into z minus z0 to the power n minus m, where n is going from m to infinity. Let's just be careful. What if m is equal to 1? Yeah, so there is a mistake. This should be n minus m plus 1. The proof of this particular exercise can be done by an induction argument, which I will leave it to you. We have already seen what f1 is, and we know the explicit expression for f1, and from that we can get hold of f2 and so on. So let me leave this as an exercise for you to check that this is indeed the case. Okay, what is the corollary talking about? The corollary is saying that the coefficients an is in terms of the derivatives of f given by fn of z by fn of z naught by. So yeah, maybe I made a mistake. I should stress upon the fact that this is being evaluated at z naught. I had not written it correct earlier. Now this is the right expression. So if we want to capture the constant term here, fm at z naught, that will be when n is equal to m in the right hand side. So this is just going to be m into m minus 1 into up to m minus 1, which is 1 into am, and this is precisely equal to m factorial times am. All other terms will vanish, and this gives us that am is equal to fm of z naught by m factorial. So the power series is completely captured. The coefficients of the power series is completely captured by the derivatives of f evaluated at z naught. Another corollary to the corollary given above is that if g of z is a power series around z naught, summation bn z minus z naught to the power n, g of z is equal to f of z in a small neighborhood of z naught. Suppose we start off with some other power series, summation bn z minus z0 to the power n, such that, oh, what is f naught, where f of z is the usual power series we were considering all along, an into z minus z naught to the power n. Suppose we know that this is equal, both these power series are equal in a neighborhood of z naught. Then the conclusion is that an is equal to bn. The proof is just one line. It is to notice that if f is equal to g in a neighborhood of z naught, the derivative, calculation of derivative is a local property. Since f of z is equal to g of z in, say, dz0 epsilon for some epsilon positive, we have fn of z is equal, fn at z naught is equal to gn at z naught for all n natural numbers, and this tells us that an is equal to bn. Since an is equal to fn at z naught by n factorial and bn is gn at z naught by n factorial, and that completes the proof. So the coefficients are the same if two parts, so the power series are the same. Basically, that's what it says. This is a special version of what is called as the identity theorem, which tells us that if two power series agree in an open set, then it should necessarily be the same. The power series are equal means that the coefficients are the same, and that's what this theorem says. We'll prove a much stronger version of this theorem later, but this is the first and the most basic version you can look into. Let's calculate the derivative of some of the standard holomorphic functions we had defined earlier, or which was defined, in fact, it was defined in terms of a power series. So consider e to the power z, which is equal to summation z to the power n by n factorial. We are just going to differentiate e to the power z, and we know that this is going to be term by term differentiation. The 0 n equal to 0 term vanishes, and we are going to end up with z to the power n minus 1 into n by n factorial, which is going to be n minus 1 factorial, which is equal to summation n equal to 0 to infinity of z to the power n by n factorial, which is again e to the power z. And with the laws of calculus, what was sine of z? Sine of z was e to the power iz minus e to the power minus of iz by 2i, and d by dz of sine of z, we know what the expression would be. That is just going to be equal to e to the power iz plus e to the power I minus iz by 2, which is equal to cos of z. You can check that d by dz of cos of z is minus of sine of z. Let us conclude this lecture by discussing product of power series. We know that from a real course on real analysis and Merton's theorem, we know that if we have an absolutely convergent series and another series which is convergent, then its Cauchy product also converges to the product of the limits. We'll recall the proof here for the sake of completion, even though it has been something which was covered in a real analysis course, especially because we want to talk about product of power series. So let me write it down as a proposition. Let f of z be equal to summation an z minus z0 to the power n. So the limit is from 0 to infinity. If I am not writing the limits, it means that it is from 0 to infinity. And g of z be equal to summation an z minus z0 to the power n, be power series which converges in dz0r. So that means the radius of convergence of both these power series is at least r. Then, so let f of z, g of z is given by the power series summation cn z minus z0 to the power n, where cn is equal to summation ak b n minus k, where k is from 0 to n, which also has a radius of convergence at least r. Which also has a radius of convergence. I'm only talking about at least r. Let's give a proof of this statement. So let me read the statement out for you once more. It says the following: if you have two power series expressions, summation an into z minus z0 to the power n, and g of z is summation an into summation, good that I read it back, summation bn into z minus z0 to the power n. If you have two such power series, then the product, the Cauchy product, which is given by this power series, where Cn is expressed in this manner, this is going to be a power series which will also converge in a disk of radius r. Let's give a proof of this. This is basically a proof of the Merton's theorem, but let's recall it for the sake of completeness. What we know is that both these series converge absolutely. We actually don't need the entire strength of both the power series converging absolutely. Nevertheless, so notice that for z in dz0r, summation an z minus z naught to the power n converges absolutely. Both this and summation bn z minus z naught to the power n, both of them converge absolutely. Let us give the partial sums a name. So let a capital AN be equal to summation AN z minus z0 to the power maybe AK z minus z0 to the power k, where k is from 0 to small n. We know that AN converges to f of z. Let's call something here similarly. Bn be summation bk z minus z0 to the power k, where k goes from 0 to n. Cn, similarly, it is defined. This is basically ck z minus z0 to the power k. K is equal to 0 to n. Our goal is to show that Cn converges to f times g at z. So the z is fixed. So for z in dz0r, a fixed z in dz0r is where we are doing all this analysis. And what do we have? Let's elaborate the capital Cn here. This is just going to be equal to a0 b0 plus a1 b0 plus a0 b1 times z minus z0 going on up to an b0 plus an minus 1 b1 plus a0 bn z minus z0 to the power n. If we capture the like terms, what do we have? This is going to be equal to a0 into b0 plus b1 z minus z0. So this is going to be a0 times bn plus, or maybe let me write it as bn times a0 plus bn minus 1 times a1 into z minus z0, going on up to bn into b0 into an z minus z0 to the power n. It's just a rearrangement of terms that was done to write it like this. Okay, let dn, I'm slowly running short of alphabets. This is going to be, what is this? This is basically bn minus g of z. Let's define dn to be bn minus g of z, and this is just going to tell us that the above expression will be g of z into a0 plus a1 into z minus z naught plus up to an into z minus z naught, and adding and subtracting gz, this is just going to be dn times a0 plus dn minus 1 times a1 into z minus z0 all the way up to d 0 an z minus z0 to the power n. So we are now ending up with these two expressions. Notice that the first one is just g of z times capital An plus dn a0 plus up to d0 an z minus z0 to the power n. If we manage to show that the thing inside this bracket converges to 0 as n goes to infinity, then we know that an converges to f of z, and therefore, so this is, notice that this is equal to cn, therefore limit as n goes to infinity of cn will turn out to be equal to g of z times f of z. So the only thing that we have to show is that this term inside the bracket here indeed converges to 0. Let's focus on that term. Consider dn a0 plus d1 a1 into dn minus 1 rather, z minus z0 plus up to d0 an z minus z0 to the power n. Notice that dn converges to 0 because dn is basically bn minus g, and therefore given epsilon positive, there exists a capital N such that dn is less than epsilon. This is certainly the case. And therefore, if you look at the absolute value of dn a0 plus up to d0 an z minus z0 to the power n, let's break this into 2. This is going to be less than or equal to, let me just reverse the order and write it in a slightly different manner. This is going to be d0 an z minus z0 to the power n plus up to dn capital N z minus z0 to the power capital N. Okay. an minus capital N z minus z0 to the power n minus capital N. This term plus the remaining terms, that will be dn plus 1 an minus n plus 1 z minus z0 to the power plus 1 all the way up to dn a0, right? By applying triangle inequality again and noticing that mod dn plus 1 is all less than epsilon, this is going to be less than or equal to mod of d0 times mod of an z minus z0 to the power n. The first part, let me just leave it as of now, let me just leave it exactly like that, not touch it now. But what follows is of interest. Here this will be less than epsilon times, let me just say that this is going to be less than mod a0 z minus z0 to the power n. Certainly going to be less than this. Let's call this, so here it will be, here it's just a finite sum, but I am going to put in a 0 to infinity here using the fact that our series converges absolutely to some number. Let's call this equal to alpha. So this tells us that mod dn a0 plus d0 a1. So what was this? d0 an z minus z0 to the power n. This is less than or equal to mod d0 mod an into z minus z0 to the power n plus all the way up to d capital N z minus z0 to the power n minus capital N, so there is an an here, plus epsilon times alpha. So notice that now on the right hand side we have capital N expressions of this type. So I think I should be a little careful here. This is going to be d capital N a n minus capital N mod z mod of this z minus z0 to the power n minus capital N plus epsilon times alpha. So notice that each of these terms which I am now underlining in green, there are capital N such terms, each of them go to 0, since these are terms which are featuring in the power series summation a n z minus z0 to the power n. So as n goes to infinity, each of these terms go to 0, and therefore what we are ending up is that limit as n goes to infinity of dna0 plus up to d0 a n z minus z0 to the power n is less than or equal to epsilon times alpha, where alpha is some fixed number, positive real number. But our choice of epsilon was arbitrary, and therefore we have this lim sup as n goes to infinity of mod dn a0 plus up to d0 a n z minus z0 to the power n is equal to 0. But then we are considering a sequence of non-negative numbers, and therefore the lim inf also is greater than or equal to 0, and therefore the limit has to be necessarily equal to 0, and that's precisely what we had to prove, which gives that the limit as n goes to infinity of a term is equal to 0. But that would tell us, let me just go up and show that we were interested in proving that this term goes to 0 precisely because we had shown that our Cn turned out to be like an expression like this. Where is the expression? This is the expression. So this is our Cn, if you notice. This is precisely the expression for Cn that we have, and limit as n goes to infinity of Cn is what we are interested in. And we have shown that this is indeed converging to f of z times g of z. So the broader scheme of things, what have we proven? We have proven that for z in dz0r, the Cauchy product does indeed converge, and it converges to f of z times g of z. So yes, this power series, it has a radius of convergence at least r, because for every z in dz0r, we have shown that it converges to f of z times g of z, and that's precisely what we had set out to prove. Let me just say that this implies that limit n going to infinity of Cn is equal to f of z times g of z. And with that, we are done.